Okay, hello everyone. We are very happy to have Naveen in today's seminar. Naveen is the Usha Hasteer Professor of Computer Science at IIT Delhi. He has been at IIT Delhi for his B.Tech and then for his Ph.D. and he has been a professor there since 1998. He was at Max-Planck-Institut in Germany for a postdoc and currently is on a sabbatical at University of Warwick, UK. His contributions are primarily in the design and analysis of approximation algorithms for NP-hard combinatorial optimization problems arising in network design, scheduling, routing, facility location, etc. And he is a fellow of Indian Academy of Science and the Indian National Academy of Engineering and was awarded the S.S. Bhattacharya Award for Mathematical Science in 2016. All yours.
Thanks, Raghuvansh. Thanks for inviting me to give this talk. It's always a pleasure. Would have loved to be there at AFR in person, but yeah, I'm away, so some other time. So today I'm going to talk about a facility location problem. And I've been talking to some folks here about clustering, and many of the same ideas are useful also for when you have set of points and you want to create clusters of those points. So in particular, I'm going to talk about facility location with outliers, and I'll define most of these concepts. The talk, tends to get a little bit technical further on, but feel free to interrupt me anytime you want to, if you're not following. So yeah. So this is joint work with the student Rajni Dabas and colleague Nilima, who's at Delhi University, and this is to appear in IPCO this year. Okay, so let's get going. Good. So what's the setting? So we are talking of facility location. So think of n points. We are going to call them clients, and some of these are possible locations at which we can open facilities, right? So the potential facility locations might be disjoint from these points, might be a subset of these points. It doesn't really matter, and you're given a metric on these points, right? Now, if I open a facility at a location I, it costs some f sub I units, right? And you can imagine that at different locations, if I were to set up, let's say my facilities were bank branches, right? Branches of a bank. And so depending upon the location, if it's a very expensive location, it is going to cost different amounts to set up that branch. So every location has a cost of setting up a facility there. And now if I set up facilities at some set of locations, then I have to serve the clients, right, from these locations where I've opened the facilities. And to serve a client J, buy a facility at location I, the cost is, let's say, Dij, right? So D, remember, is a metric. So it's the distance between I and J. And this captures, the cost could be thought of in many different terms, right? It could be, the distance a person has to travel. It could be some other notion of cost, right? Maybe this is a computer network and this person has to connect to this particular facility in some manner. So we'll not really specify. The only thing that we need to know is that D is a metric. And that's going to be important for our discussions. And what's our objective? It's to open facilities so that the total cost of opening the facilities, which is basically summation Fi for the facilities that I opened, plus the total cost of serving all the clients, that is minimized. So note that if I do not place any other restrictions, then every client will go to the nearest facility, nearest in this nearest facility which is open, right? if I had not placed any kind of further restriction, but I'm going to be placing further restrictions, and so that thing need not necessarily hold. The outlier version of these problems is that I don't have to serve all clients. I'm allowed to not serve some small O number of clients, right? And these will be the outliers. And these are increasingly in many clustering applications, having this provision of outliers is an important idea. I remember many years ago, I worked with some colleague at IIT Delhi who is in the textile engineering department, and there what we were trying to do was to create clusters of garment sizes, right? So the setting was that we had body shape measurements of a large number of people, and we wanted to find out what is the, let's say, smallest number of sizes of a particular garment that we would need to fit all of these people, right? Where fit was defined as, of course, a ready-made garment cannot exactly fit a person, but within a certain tolerance, right? So I'm not saying this is an example of this, but what we learned from that exercise, or at least I learned from that exercise, was that it was very important to discount some outliers, because there will always be outliers in any population, and if you try to tailor your algorithm to handle all clients, it can give you solutions which are very weird and very meaningless. So, and increasingly outliers play a very important role, or discounting outliers becomes very important for a lot of applications. So this talk is going to be addressing some of these issues. I'll quickly go over this. The idea of outliers has been considered in the facility location community for over 2 decades. I think one of the earliest papers was by Charikar, where he considered facility location with outliers, and they gave a 3 approximation. And more recently, there was work by Ravi Krishnamurthy and some other colleague, Krishnaswamy and some other colleagues on K-median with outliers. So in the interest of time, I'm not going to define what the K-median problem is. It's not going to be very relevant for this talk. But for the purposes, yeah, so I think all you need to know.
I think Ravi is speaking here in 2 weeks, so we can ask him.
Yeah, sure, go ahead.
Good. I'm saying Ravi is speaking here in 2 weeks, so we can just ask him.
Okay, good. Sorry, I didn't quite get you. Okay, yes. Yeah. So I do not know if he's giving this talk, but this was a very nice result that they had maybe 5 years ago. I don't remember the dates. Yeah. Great. So now let's also bring in capacities, right? Now, again, whenever you're talking of facility location, a capacity does make sense, right? I said every client would, if you did not have any capacity restriction, then every client would just go to the nearest open facility, right? But you can imagine if this is a facility like a bank or a post office or anything, right? It has to have a capacity in the sense of how many clients it can serve per unit time or some such thing. And so we will have U of I denote the number of clients that can be served by a facility at location I. And so this is what's called the capacitated facility location problem. If all these capacities are identical for all the facilities, then there is a 3 approximation that is known. And if the capacities are not uniform, they're non-uniform, then there's a 5 approximation more. So it has been considered capacitated facility location. And so what we are going to be doing in this talk is we are going to be considering capacitated facility location with outliers. And this is something that has not, people have considered it before without success. So this talk is sort of, this result of ours is the first approximation algorithm for a facility location problem that has both capacities and outliers. together included. And the challenge with these problems is that, both of these are hard constraints, right? You can't violate capacities. You can't say that, okay, you're allowing me 10% of the outliers. I'll give a solution which has 15% outliers. So if you do not allow for any violation in capacities or increase in the number of outliers, then we say it's a hard constraint, and then designing algorithms becomes quite challenging in these settings. Okay, sorry, I should have shown the slide. So in this talk, I'll show one simple improved approximation algorithm for a specific setting. So, okay, so the one thing, and I did not mention this here earlier, we will have to, in designing this algorithm, we will have to assume that the facility costs are uniform. So we're talking of three things now. So remember, we had facility costs. So earlier I'd said at location I, the cost of opening a facility is F sub I. So it depends upon the location. And I had also justified that, but now I'm going to walk back on that and say, let's assume facility costs are the same. The second thing is every facility has a certain capacity. So we are going to have capacities, and we are going to also allow for some clients not to be served, right? So outliers. So what I'm going to show you is first an algorithm for uniform facility costs and capacities, non-uniform capacities without outliers. So I'll give you a simple algorithm for that. And this also improves on what was known earlier. So this is the first result here is without outliers. And in the second part of the talk, I'm going to show you a constant approximation when you also bring in outliers into the setting. Yeah. So yeah, I guess everyone sort of is clear on what the problem is and what I'm going to be showing in the talk.
So Naveen, so for the second problem, you have non-uniform capacities, uniform facility costs, and outliers. Is that correct?
Non-uniform capacities, uniform facility costs, and outliers. That's right.
Okay.
Right. So the sacrifice we have to make, and that is also, I leave that as an open question for future research, is we have to sacrifice non-uniform facility costs. And you'll sort of see why that is needed, right? We have to sort of amortize over facility costs, and then, yeah. So we have to assume that they are uniform. Yeah, I'll just go on with this one then. So I'll show you the first, the simple algorithm when we don't have outliers. So what do we have? We have uniform facility costs and non-uniform capacities, right? And I'll show you a simple algorithm for that setting. Okay, so let's understand what does a solution mean, right? So I give you such an instance. I claim a solution is completely specified if I tell you what set of facilities that you are going to open, right? If I say, okay, this is the set of facilities you open, that sort of determines what is the cost of servicing the clients. And of course, if I tell you which facilities are being opened, that also tells you the facility cost, right? So how would you do that? Remember, facilities have capacities on them. So you have to find an assignment of clients to facilities. So I've told you what facilities are open. So you have to find an assignment of clients to facilities respecting the capacities. So now, because you have these capacity constraints, it will not be the case anymore that every client would go to the nearest open facility, because you might have everyone going to the same. So, but you can see very easily that you can formulate it as some kind of a min cost flow problem, right? Think of the clients, think of a bipartite network where clients are on one side and the open facilities, the facilities that you are opening on the other side. And there is an edge from a client to a facility which can carry 1 unit of flow and has cost equal to the distance between the 2 points, between the client and the facility. And the capacities on the facilities can be modeled by having an edge from the vertex corresponding to the facility to a sink vertex of capacity equal to that capacity, right? So you connect all your clients to a source, and now you are trying to send a flow of n units, because n is the number of clients, from the source to the sink of minimum cost. The cost is coming from the edges that are between the clients and the facilities, and this will give you the best solution. So all I'm trying to say through the slide is that if I give you the set of facilities that are open, you can determine the assignment, right? So I don't have to give you the assignment. I just have to give you the set of open facilities. And ditto for outliers, right? So if we were the outlier version of the problem, and I said you are allowed some O outliers, then the way to do it is actually I'll create an outlier, one facility on the right hand side. So remember, I talked of this bipartite network: one side clients, one side facilities, or the facilities which I am opening. And besides the facilities which I am opening, I'll also have one vertex for an outlier facility. And this has capacity O, because that's the number of outliers it can handle, and it has distance 0 from all the clients. So there are edges from this vertex to all the vertices on the client side, and the cost of those edges is 0. Right? So once again, you can think of this for a minute and see that if I compute a maximum flow from source to sink, then you would want to, because you're getting 0 cost by sending flow to the outlier facility, but you can only do that for at most O clients, right? Because that's the capacity of that edge, right? So again, so this is just saying that given the set of open facilities, everything can be determined. And so we are going to use C sub S to denote the service cost, C sub F to denote the facility cost, and C of S to denote the sum of these two, the service and the facility cost, if I open a set of facilities capital S, right? So a solution is specified by the set of open facilities I open, and C sub S is the service cost and C sub F is the facility cost. Facility cost, remember, is just trivially just summing up the cost of the facilities in this set S. So it's quite straightforward. Okay, and now I'm ready to give you an algorithm, right? And it's going to be a local search algorithm, so really very trivial. So let's say S is the current solution that I have. So in a local search algorithm, I'm sure many of you would have seen an algorithm before, such an algorithm before. So you have a certain solution, and you see if there is a move or a change that I can make to the solution, which will improve the cost of the solution, right? And you keep doing this till you cannot make any changes anymore, till you cannot improve the solution anymore, and then you stop. And when you stop, you get what's called a locally optimum solution. And so what we'll be doing is I'll be showing you what the potential moves are at every point. And when you stop, we'll argue how bad the locally optimum solution is compared to the global optimum, compared to the optimum solution overall. One question that arises is running time. Sorry, go on.
So just the previous slide, the CS of S that you defined, service cost, that's not submodular, right? Do you know, like, does that have nice properties? Do you
know? The service cost is no, the service cost. So your question is it a submodular function?
Yeah. Yes.
Is the service cost a submodular function? I guess a submodular function of S, right? So yeah. If I add, No, see, the sum actually, it's not even a monotone function, right? No, in fact, it is, sorry, it is monotone, right? So if I increase the size of the set, the service cost only decreases. It's monotone decreasing. And now your question is it submodular?
Wait, I mean, we can go on. I just thought.
Yeah, let me, I'll hopefully by the end of the talk, I should be able to answer.
Wait, I also have a question. So
Yeah, go on.
I thought you said that there is a need for the distances Dij to be a metric space, something like
Right.
that.
Yeah.
But when you add something with distance 0 to all the clients, does that not violate this property?
That's true, yeah. So that was only for the purposes of computing. So I'm not saying that that's what I'm going to be doing for. So I'm not going to reduce the outlier version of the problem to the non-outlier version by that trick. So that's not what I'm saying here. I'm saying that to find the assignment, to find the best assignment of clients to. So if I told you what the open facilities are, right? Then that doesn't give you the entire solution, or you would feel that that doesn't give you the entire solution because you still have to tell me which are the outliers and which are the so which client is assigned to which facility, right? So in here, all I'm saying is that can be figured out by just giving you the set of by solving this min cost flow problem, right? So, but I'm not saying that I'm solving the outlier version of the problem by creating a new facility with capacity O. So that's not, so I cannot do that because exactly for the reason that you said, it would violate the metric property if I were to do such a thing. So this thing is only to be able to compute the cost of a solution S, right? That's all. And that can always be done, right? So,
Okay.
Did I answer your question?
Yeah.
Yeah.
Sorry, I had one more
Yeah.
question. So this,
Sure, go ahead.
this second operation, this open operation, is that
Yeah.
a one-time thing? As in, like, if I give you a new facility U, and you figure out if there exists an S prime, which upon removing will reduce the cost?
Yeah, good point. I still have not reached that point on this slide, so let me come to that. So let's go over this. What are the operations that we are defining here? So S is our current solution, and I'll look at. So there are only two operations that we consider. One is an add operation. So S is the current set of open facilities, and I see if there is some facility not in S, which when added to S improves the cost of the solution, right? So note that when I add a facility to S, the total facility cost will increase, but the service cost, the cost of serving the clients will decrease, right? Because this new facility that I added can be serving some clients at a reduced cost because maybe it's closer to, right? So it's like a new bank branch opens and then some clients will benefit from it because they will have to travel less. So there's a trade-off here, right? So one aspect of the cost increases, but the other aspect decreases. And so if by adding this, the total cost decreases, then I will make this move. And now coming to the question that was asked, there's another operation which we call open, where you take a facility U and you add it to S and you shut down a set of facilities S prime, right? So S minus S primes, where S prime is a subset of S. So you shut down a set of facilities S prime, and that's your new solution, right? Okay, so the question that was asked was, can you figure out the best S prime to shut down? The answer is no. Yeah, so that itself is an NP-hard problem, finding out the best S prime to shut down. But what we will do is that we'll not be finding the best S prime. We will be finding a S prime to shut down. And if by shutting down that S prime and adding this U, the cost of the solution improves, I am going to be making that move. And what we will argue is that for purposes of analysis, we don't need the best S prime. We just need our definition of S prime, and that is sufficient for to analyze the algorithm. Yeah. So yeah, we can't find the best S prime because it's NPR. Okay, so let me show you how these analyses are done, right? And this is a fairly simple setting, so we should be able to go over this fairly quickly. So remember, okay, so now I've run this algorithm. So this is the entire algorithm, right? You start with some arbitrary initial solution, and you either add a facility or you do this open operation. Now, some of you might be wondering that there doesn't seem to be any operation for closing the facility, right? Because you might have initially started with a solution S which includes all the facilities, right? All possible facility locations. So you should have something to shut down things. And the shutdown is happening intuitively in this way also, right? So in here in the open operation, I have not specifically said that U is not in S. So this U could be belonging to S, and I could be shutting down, when I'm shutting down S prime, I could be shutting down U together with some other people, in fact. So this, it's a bit devious, but maybe not the best way to say it, but this operation also captures, closing the facility. So let me bound the service. So we ran this algorithm, we obtained a locally optimum solution. And now let me, so what does it say when I have a locally optimum solution? It basically says that I cannot improve the solution by any of the two operations that I have. Okay, and now let me use this fact that it's a locally optimum solution to bound the service cost of the solution, right? And that's what I'm doing on the slide. And it's a very simple argument. And so let me show how this proceeds. So we are only going to be using the add operation, right, to do this analysis. So remember, what is the add operation? You add a facility S, and you find the best assignment. So the facility S that you are adding, so you find the best possible assignment. And if if the total cost of the solution decreases, you add this facility. So let's, in this figure that I have here, in this picture, the blue dots which are in the center, they are the clients, C. And the green diamonds that I have at the bottom are the facilities in my solution S. Okay. And the orange arcs show which client is served by which facility in the solution S. So every client is served by one facility. Right? Now, I'm going to take so for the purposes of this analysis, or for the purposes of this presentation, I'm going to assume that S is disjoint from S star. S star is the optimum solution, right? And I'm going to consider the facilities of S star one after the other, right? So this red square that you see in the top row is a facility in S star. Now remember, I could have considered this facility in my add operation. I did consider it, but it did not give me an improvement in the cost. And so I did not, it would not have given me an improvement in the cost, because if it did, then this solution S that I had was not a locally optimum solution. So when I added this facility, there was I could have done, so maybe in the optimum solution, this red facility of S star is serving these clients, and I'm going to use numbers to refer to the clients. So from the left, I'll call clients 1, 2, 3, 4, and so on. So this red facility is serving clients 1, 2, and 4. right? So in the optimum solution, of course, I do not know this, right? But now consider an assignment. So when I added this facility, remember, I'm finding the best possible reassignment of clients to facilities. And one of those reassignments would have been that these clients 1, 2, and 4 were served by this new facility that was added, right? So the service cost of these clients would have changed, right? So these clients would not be served by the green diamond facilities that they were being served by, but instead they would be served by the red facility that I added. So this, of course, causes a change in the service cost. And what is the change in the service cost? The change in the service cost is that the red arcs at the top, I'm going to be counting those distances. So this is and I'm going to be removing the distances. So the new cost minus the old cost will have the red arcs at a plus and the orange arcs at the bottom with a minus. Right? Does everyone see the red and the orange, or is it only on my screen? Because your projector might be.
No, we can see it. We can see it.
You can see that, yeah. Maybe there should have been a stronger contrast of colors there. Right? So everyone understands. So when I write the inequality for this, I've also put a plus on the red square, right? So the inequality would say, so what is the new cost? The new cost would be the facility cost of this red vertex, this red square. So that's why there's a plus the lengths of these red arcs. Yeah. This is the new cost. Of course, the change in cost. So new cost minus old cost is what I'm calling the change in cost. So the change in cost will have a positive term for the facility cost of the red square. It will have a positive term for the red arcs, and it will have a negative term for these orange arcs, for these 3 orange arcs only, not the others. Right? This is if I did this reassignment. Of course, I'm doing the best possible reassignment, right? So if the best possible reassignment, if for the best possible reassignment, the new cost was still more than the old cost, then that means that for this reassignment too, the new cost was more than the old cost. Yeah, because the best possible reassignment is the one in which the new cost is the smallest. Right? So for this specific reassignment that I chose, these plus terms will be more than the minus terms. Yeah. Does everyone follow me here? So I've not put down the inequalities because it's sort of become intimidating, but I hope with this. So since I say locally optimum, the plus terms exceed the minus, right? For this particular facility. And now we can repeat this for all the others. Right? I consider the next facility in S star and I do the same thing. Right? I'll have a plus associated with it and plus associated with the facilities with the clients, the distances from the clients to that facility, the clients which are served by this facility in the optimum solution. So there'll be these pluses and there'll be the minuses for the distances of these clients to the facilities that serve them in our solution, right? And so we'll have all of these. And now if you look, and I'll write down all of these inequalities and I sum them up. And when I sum them up, I'll get this picture, right? So basically the sum of all the pluses exceeds the sum of all the minuses. Now, if you look at all the pluses, what is that sum equal to? That's exactly the facility cost of the optimum solution, right? Because I have a plus associated with each of these facilities here, plus the service cost of the optimum solution, because in the optimum solution, these red arcs are the arcs corresponding to which facility. Yeah, so are arcs corresponding to the service cost, right? This client is served by this facility and so on. So the pluses are exactly the service cost and the facility cost of the optimum solution. And the minuses are the service cost of my solution. So since the plus terms exceed the minus terms, we have that the service cost of my solution, okay, there should have been a CS, right? So there should be a subscript S below the C. So CSS is less than CFS star plus, or service cost of my solution is less than service cost of the optimum solution plus the facility cost of the optimum solution. Right. So just using the add operation, we are able to bound the service cost of our solution. Right. In terms of the optimum solution. Now, the other part where we have to, so now we also have to bound the facility cost of our solution, right? Remember, the cost has two components to it: the cost of servicing the clients plus the cost of opening the facilities. And so now I have to bound the cost of opening the facilities of my solution. And there I'm going to be using the add operation that, so the open operation that we had, which was a bit weird, right? So we said we are going to take a facility U, include it, but then shut down a set of facilities, right? So that the reduction in cost is max. Okay, we said we can't do maximum, but we nevertheless want to identify a subset, a good subset, right? And so that's what I'm going to show you next. How do I identify this good subset of facilities to shut down? And I'm going to make an assumption here. And the assumption, and this is a critical assumption, which will let me find this subset, or find such a good subset. It's not the best subset, remember. It's not the best subset because I'm going to be making a certain assumption about this subset. So we are saying that when I shut down this subset S prime, we'll estimate the cost reduction by assuming that all clients served by facilities in S prime will now be served by this facility S. Which is this facility S? This is the one that I added. Okay. So if I make such an assumption, that remember we also have capacities on our facilities. So if I make such an assumption, then one thing that follows is that the total capacity or the total number of clients served by S prime should be less than the capacity of this facility S that I'm adding. Right? Because we are saying that all the clients that are served by S prime will now be served by little s. So that's one thing. And now with this assumption that I've listed here, I can find the best set S prime by solving a knapsack problem. And I'll show you how. Right? So let's say this is this. So I'm going to be iterating over all possible choices of little s, right? So there's this little s that I decide to add. And I have now to find out the best S prime that I should remove, that I should shut down. And remember, S prime is a subset of the set of facilities I already have. So it's a subset of S. So I'll go through all these vertices of S and I'll compute some quantities for them. Right? So in particular, when I'm considering a facility I in S, I'm going to say, okay, if this facility I was included in S prime, then right now it is serving 3 clients. All these 3 clients are going to be served by S. That's the assumption I have made. And so what is the reduction in service cost that I'm going to get? I'm going to denote that by the quantity Ri. Right? So the reduction in service cost, if I were to shut down I, under the assumption that all the clients that are served by I will now be served by S. So the reduction will be what? So for this client, there is a reduction of 3 units. For this client, there is a reduction of 4 units. And for this client, there is a reduction of another 2 units. And so the total reduction is 9 units in cost. And so R sub I is, so this is the reduction in cost in the service cost. And because I'm shutting down I'm also shutting down, I don't have to pay its facility cost anymore. and I'm under the assumption that all facility costs are uniform and are F. So I'm going to just add F to it, right? Because I'm going to be shutting down this. So that's a total reduction in cost, right? The first, the 9 is the reduction in service cost, and the F is the reduction in the facility cost if I were to shut down I. And now I have to find the best set S prime, right? So I have to figure out which are the facilities that should belong to S prime. So this facility I gave me a reduction of 9 plus F. Why is this a knapsack problem? So I'm getting a benefit of 9 plus F, but I am taking up, so remember I had said earlier that all these 3 clients will have to go to S, but S has a capacity only of 6, right? So I can't just, so I have to pick up such facilities such that the total number of clients they will send to S when they are shut down doesn't exceed 6. So I'm modeling it as if I have this object, for every facility I have an object of value, so equal to the reduction Ri. So for corresponding to I have an object of value 9 plus F and of weight 3 being the number of clients it was serving. And now I want to find a subset of objects of total, of maximum total value. Remember the value was the reduction. So maximum total value and total weight at most 6, where the weight of an object is the number of clients it is serving. So suppose facility I serves SI clients. So that's exactly what I've said here. Then we want to find S prime such that summation SI is at most 6, because that's the capacity that S has. And summation Ri, which is the reduction, is maximum. And this, as you can see, is a knapsack problem, which can be solved. Knapsack takes time, that is pseudo polynomial in the total weight, but the total weight here is just the capacity of this, which is no more than n. So you can get a polynomial time algorithm to solve this knapsack problem. So going back, that's how we are going to find this this set S prime for every S, right? This is our notion of the best S prime. So it is best under that one assumption I've made, right? That if I shut down a facility, if I include a facility in S prime, then all its clients are going to be served by the facility that I've opened, the new facility that I've opened, little s. Okay, so any questions till this point? Okay, so now things get a little bit more technical, and I'm going to try and see how much I can accommodate it in the next 5 minutes. So how do we do this analysis now? So I told you the operations. I've also told you how to implement the operations. I've also told you how to bound the service cost. Now we are in the game of bounding the facility cost of our solution, right? And to bound the facility cost, I'm going to build a graph. And this we'll call a exchange graph. So on one side of, remember this is roughly the same picture as you've seen before. These blue circles are the clients. S star are the facilities in the optimum solution, and S is the facilities in my locally optimum solution. So the green are the facilities in my locally optimum solution, red are the facilities in the optimum solution, and blue are the clients. And what are these arcs? So for every blue client, there are 2 edges, one to the facility in S star, which serves that client, and one to the facility in S, which serves that client. Okay, and now from this picture that I have on the top, I'm going to extract this picture at the bottom. And the way I'm going to extract this picture at the bottom is, if, so it does not have, the picture at the bottom does not have any of these blue clients. And it's in some sense like a short circuiting. If I have a blue client, for every blue client, I look at the red facility and the green facility, and I put an arc between them. So for instance, on the leftmost blue client, contributes one arc between the leftmost red facility and the leftmost green facility, and so on. So here I have labeled this arc 2 because there are actually two blue clients which are served by the same facility in S star and the same facility in S. So I've labeled this arc 2. Okay. Now this is a graph. I'm going to call it H, and I am going to assign every edge of this graph a value, a number X, which is this edge, which is labeled 2, has an X value of 2. All other edges have an X value of 1. Okay. Now, if you think of it for a minute, then for any vertex, any green vertex, and that's any red vertex, that's 0.2. If I sum up the X values of the red vertex, some of the red values of the edges, of the X values of the edges incident at that red vertex, what will that be? Right? For this leftmost red vertex, it's going to be 1 and 1, 2, which is exactly the number of clients that was served by this facility in S star. And for this rightmost red vertex, it is 2 plus 1, 3, which is exactly the number of facilities. And so that should be easy to see. So sum of X values of edges incident to a red vertex is exactly equal to the number of facilities that vertex served. And similarly for the green vertex. What is also interesting is this claim at the bottom, which is saying that if I take X value and multiply it by the distance, right? So take the X value of this edge, which was 1, leftmost edge, and multiply the distance by the distance between that red vertex and the green vertex. And I sum this over all the edges, right? So multiplying it by the distance, and here is where I'm using triangle inequality. Remember, this distance is only less than the sum of this distance and this distance, right? I hope you can see my pointer.
Yeah.
You can, right? Okay. So it's only less than the sum of these distances, which means that when I do this, X times D, I am summing up all the distances in the picture on the top, right? Which is just the service cost of S star plus the service cost of S. Right? Now, what I'm going to do is I'm going to make this graph acyclic, this graph H acyclic, by modifying X suitably. The modification to X that I'm going to be making is such that it will still preserve all of these three properties. Note that this graph is not acyclic, right? I have a cycle here. What I can do is I can go around, I can take this cycle and I can increase alternate edges on this cycle by an amount, in this particular case by an amount 1, and decrease the other edges. So the cycle will always be even, by the way, because it's a bipartite graph. And so I'll take this even cycle and take alternate edges, increase them by 1, and the other set of edges I'll decrease them by 1. When I do that, note that these three properties, the first two properties will definitely be maintained. And the third property need not be maintained. But if it is not maintained, then I could do the reverse change, right? So let's say I took this edge to increase and this 2 edge to increase to 3. So I increased 1 to 2 and this 2 to 3, and I decreased these 2 1s to 0. If this does not cause a if this does not cause a reduction in this left-hand side, then the other direction would cause a reduction in the left-hand side. Okay, which means what does that mean? That means that I decrease this from 2 to 1 and this from 1 to 0 and increase both of these from 1 to 2. That will cause a decrease. So I'll always pick that direction which causes a decrease. And so I can always make this change so that one edge goes down to a 0. When an edge goes down to a 0, I'll remove it. And I can keep doing this for every cycle and make the graph acyclic. So when I'm done, I'm getting these quantities X, which don't make any sense anymore because now I've done some weird changes to X. Initially, they made sense, right? But they will have these nice properties, and that's all we need. And I am almost out of time. I am out of time. So I'm going to sort of quickly say what we do next. So we take this acyclic graph. we route it. So if it's acyclic, it's basically a forest. For every tree in the forest, I'm going to route it at a certain vertex, and a certain vertex in S, so which is a green vertex. So there's this rooted, you see this rooted tree. And now remember, I have to bound the facility cost, which means the the facility cost, and here I'm using the fact that facilities costs are the same. So I have to bound the number of green vertices in this. And the number of green vertices, the way I'm going to bound them is I'm going to say, okay, the number of green internal vertices is going to be less than the number of red vertices. Right? Okay, by the way, every green vertex has a red vertex as its neighbors and vice versa, because it's bipartite. And the other green vertices, which are leaves, I'm going to bound them. And so this is the triangles I've shown. So these green vertices, I'm going to bound them by doing an open operation on this red vertex, right? Now here I'm using the fact that this solution that I have is locally optimum with respect to the two operations that I had added the open operation. So I'm focusing on this triangle here, and there's this red vertex and these two green vertices. And now I'm going to say the following, right? If I had in the open operation, if I had included this red vertex from S star and shut down these two from as part of S prime, then it did not lead to an improvement in cost, right? And that's the information I'm going to use to say that the total cost of the total number of these green vertices is less than the total number of these red vertices plus the service cost and the facility cost plus the total cost total x times d value of these edges in this tree. So I realize I'm a bit rushed here, but that's perhaps, I think that's because I'm out of time. But if you followed the argument until this part, it's sort of, I'm sure you'll be able to complete it in a fairly straightforward manner. So that's what we do, and this is the argument for the non-outlier version. And when you have outliers, things get messier. And we still work with the same operations. The add is the same as before. Again, it's a local search algorithm. But instead of, remember, we had in the open operation, we had that I added one vertex and I closed down a set of vertices. Now I'll have to add two vertices and close down a set of vertices. And the reason for these two is more technical and perhaps won't have time to go into it. But again, this can be done using a knapsack-like operation. Instead of a one-dimensional knapsack, we now have to do a two-dimensional knapsack. And we can do this operation and we can get a locally optimum solution. And I'll skip this. This is showing how you can bound the cost, the service cost. And the key idea here is, remember earlier in the two solutions S and S star, in the two solutions S and S star, the set of clients that are getting served might be different, right? Because we have this problem of outliers. So in S, the yellow vertices here are outliers, while in S star, the green vertices here are outliers. And so what we have to do is we have to set up some kind of a mapping between the green and the yellow vertices, a one-to-one mapping, so that any argument we do on the yellow sort of gets translated to the green. So briefly, that's the argument. And we can once again, as we were doing for the non-outlier case, argue that the total service cost is less than the total of our solution is less than the total service cost of the optimum solution plus the facility cost of the optimum solution. So this remains as before. And this argument is not hard. So pretty much right. What is harder is bounding the facility cost. And I said now we have to have this open operation. We are opening two facilities and closing down a bunch of facilities. yeah, I'm going to not be able to go into any details on this right now. This the key idea, the broad idea is still, building the exchange graph and building the tree. So many of those ideas carry over, but because of the fact of outliers, we have to do a little bit of, we have to set up some mapping between the set of outliers in our solution and the set of outliers in the optimum solution, and so on. And that gets a bit trickier. And yeah, as I said, we have to do similar things. So eventually we are able to show something like the facility cost of our solution is 5 times the facility cost of the optimum solution, plus the service cost of our solution, plus the service cost of the optimum solution. Earlier, this was 2 times, and now this worsens to 5. And so, if we put all of these things together, so we bounded the service cost in this manner, the facility cost of our solution is 5 times the facility cost of the optimum solution plus the service cost of our solution plus the service. So if I add these things up, I get that the total cost of my solution is 7 times the facility cost of the optimum solution and 3 times the, right? So just a little bit of algebra, so this of course means that it's at most 7 times the facility cost, the total cost of the optimum solution. And then there is an idea of scaling that has been used in the literature in the past, where you can scale the facility costs, multiply them by a certain multiplier so that you get these two constants balanced. And using that idea, you can get a 6.37 approximation. So this is for the problem with outliers, and for the problem without outliers, this is the bound we were operating, and we get a 3.73 approximation. So I am out of time. In fact, I'm also out of the question times, but nevertheless, if you have questions, I'm very happy to answer. These are open questions that I leave for you to think about if you're interested. Yeah. The non-uniform facility cost, it seems very hard. And, we were able to do this using local search, using LP. We have no idea how to go about this. There are strong LP relaxations known for the capacitated facility location, and also for the outlier version, but seems very hard to put these two things together. So that would be another very interesting open direction to look at. Okay, I'm going to stop.
Question also, yeah. Let me tell the algorithm which you showed, like the first algorithm without the outliers.
Right.
Is it trivial to see that the algorithm terminates quickly when you're both adding and removing, or?
Right. So in all of these local search, the way we argue termination is we say that we will make the local move if it reduces the cost by a certain factor.
Okay.
By a certain multiplicative, which is not just an improvement in cost, because the improvement might be very tiny. We say, let's say a 1.1, it improves by 10%. And so, because the cost is bounded, you start from some solution, you start, and the gap is at most, let's say n or some such thing. You can say that you can't have too many iterations you've done. Yeah, so that's the standard way we use for bounding termination.
And did you start looking at the outlier question first, or did you come up with the greedy algorithm first and then kind of observe that you could extend it to outliers? Or
what? No, we started looking at outliers first, and then it was getting very messy. And we did have a solution, but then we saw that whatever we were doing also applied to the non-outlier version, and we sort of abstracted that thing out. So it helped us with our presentation, because we could say, okay, for the non-outlier version, this is a very simple algorithm. It is also improved on the existing bounds then for the non-outlier version, and so we got and so we first came up with outlier, but it was good to encapsulate the ideas for the outlier version, for the non-outlier version separately.
And this second step that you did, not the add step, the replace step. I forget what you called it.
Right.
If you could do that optimally, would that give you a better approximation algorithm? Do you know?
No, unlikely, because I don't know how to use it in the analysis. Even if you gave me an optimum way of doing things,
Okay.
yeah, I do not know how to use it. Yeah, so just on the face of it, it doesn't seem like that would benefit. We have not, yeah, I guess that would also be something to think about. We did not think along those directions, but for many local search algorithms, one can also come up with examples showing that the analysis is tight. So we've not done it for this particular problem, but yeah, that would be also a good thing to come up with. Yeah.
Okay, so if there are no more questions, then let's thank Naveen again.
Thank you. Thank you.
Okay, we have a pleasant feedback from us. Useful.
Sorry, come again? I missed you.
I have a pleasant feedback and we'll see you soon, hopefully. So see you
Yeah, certainly. Okay, bye-bye.
Okay, all right. Let's close the session now.